Hi, Algebra 2. Wanted to take a little bit of time today to cut a quick video and just go back over a couple of the key items from our notes today and a couple of the examples that we looked at from the Math Excel. I recognize that today's topic was really kind of challenging and maybe not super clear. And I know we didn't get a chance to try enough practice together during the notes. And so I wanted to have an opportunity for you guys to be able to go back and look at these things at your own pace as many times as you need. So one of the things that we talked about was this idea of squaring and square rooting being inverse operations, that they undo each other. So here on the screen, you can see the square root of x squared is equal to x. When I take the square root of something that's squared, I get the base. And we said if you think about the definition of square root, that makes sense, right? 5 and -5 are square roots of 25 because 5 squared equals 25, right? So y is a square root of x if y squared is equal to x. And then we said, we've got this square root sign, which has a technical name in math. It's called a radical. And the expression inside the radical is called the radicand. We moved on beyond that. We said, is there other kinds of radicals? And it turns out that there are. So if we think about, can we undo something like raising to the third power? So 2 to the third power we know is equal to 8. What if we said, hey, is there a way that we could have some type of symbol that lets me undo that process? And we said, okay, here's what we're going to do. We're going to take that radical sign, but we're going to take this exponent and indicate it on the radical, here in kind of the crook of the radical. And this is what's called the index. Okay, so the index is 3, and that tells me I'm taking the third root. See, the third root of 8. So the third root of 8 is equal to 2 because 2 to the third power equals 8. And so in general, here's what we can say. A is an nth root of b if a to the n power equals b. So n is just a variable that we're using to stand for whatever the exponent is. And so when we say the nth root, it sounds a little odd, right? But rather than a square root, we know we have third roots, fourth roots, fifth roots, whatever the case might be. We did mention that the properties of roots that you learned earlier all still apply. So if I were to take a radicand and split it into two factors, each could get its own radical. If I have a quotient underneath a radical, a fraction, then I could split that so that the numerator and denominator each get their own individual radical. So here's the example that we took. We said I have the cube root of 27x to the fourth, and I need to simplify this. Just like we did when we were working with square roots, I'm going to write two radicals. This one is going to contain all my perfect cube factors, and then my imperfect factors are going to go here. So I look at 27, and I recognize that 27 is 3 times 3 times 3. Okay, so 27 is a perfect cube. It's going to go in my perfect cube radical. X to the fourth. X to the fourth is x to the third times x. X to the third is x times x times x, right? So x to the third is a perfect cube. So what do I have left? 27 goes in my perfect radical. 3 of the 4 copies of x go in my perfect radical. I have 1 copy of x left over. That's going to go in my imperfect radical. Why would I want to do this? Because this is now the cube root of a perfect cube, right? 27x to the third is the same as saying 3x times 3x times 3x, right? So the cube root of 27x to the third is 3x. Then I have a third root of x, which I can't simplify any further. So this is how this would simplify down. I want to push the ball ahead a little bit. We also talked about fractional exponents. So we talked about an expression something like this, 16 to the 1/4 power. Okay? Our understanding of exponents, like I get the base used as a factor this many times, but what does a fractional exponent even mean in that in that context? Like, how do we use 16 as a factor 1/4 of a time? So what we want to recognize is this 4 down here in the denominator, that's actually my index. That's telling me to take the fourth root of 16. Okay, so when I see a fractional exponent, a rational exponent, it's really just another way of writing a radical. These two things are equivalent expressions. And why would we want to do that? Why can't I just use the radical sign? Well, it turns out that these rational exponents have all the same properties of exponents that you learned back in Algebra 1. So if you multiply powers of the same base, we're going to add the exponents. Divide powers of the same base, we're going to subtract the exponents. Power to a power, we multiply the exponents. If you're taking a product to a power, then the power applies to each factor. If you're taking the quotient of a power, then that exponent applies to both the numerator and the denominator. Right? So what I want to do then is go on ahead and take a look at a couple of the examples from our Math Excel assignment. So here was one of the examples that we had. 243 to the 1/5 power. So remember, what this is really saying is, what is the fifth root of 243? Another way to ask that is, what value can I multiply by itself 5 times that equals 243? And I know that we don't have these memorized, right? Your perfect squares, you memorize those like literally in grade school. And your Algebra 1 teacher probably had you memorize 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 196, 225, 256, 289, 381, and 400, right? So we're not going to memorize fifth powers, but one of the things we can do is we recognize in a question like this, it's going to be an integer. So what's 2 to the fifth power? Well, 2 times 2 times 2, that's 8, times 2 is 16, times 2 again is 32. This is more than that. How about 3? 3 times 3 is 9, times 3 again is 27, times 3 again is 81. 81 times 3 is 243. Okay, so that works. Okay, 243 is 3 multiplied times itself 5 times. So what that means is the fifth root of 243 is 3. And we go ahead and we put that in. It tells us excellent work. And let's look at the next question. I'm going to jump on over this one. We broke this one down in class a little bit, but what I did want to look at again is a problem like this. So in this case, we were given square root of 11 and then the eighth root of 11, right? And it says simplify the answer, including any radicals. Use integers or fractions for any numbers in the expression. So what they're saying is they don't want us to write this as a radical. They want us to rewrite this using rational exponents. Like, would it be easier if they asked that in the directions? Absolutely, but they didn't. So part of your job is to kind of decode what the directions say. So here's what we have. I know that the square root of 11 is 11 to the 1/2 power. And the eighth root of 11 is 11 to the 1/8 power. So now I'm multiplying these two things together. So I'm multiplying two powers that have the same base. When I do that, I know that I can add the exponents together. 1/2 plus 1/8. Well, to do that, I need to have a common denominator. Well, I recognize that 2 times 4 is 8, so 1 times 4 is going to give me my numerator. So 1/2 is 4/8, and then 1/8. I add those together, I got 11 to the 5/8 power. So again, same story in Math Excel. I did type 11 and then tell it to make an exponent and then tell it to make that exponent a fraction and then go 5 over 8. And then check my answer and it says, yay me. All right, there was one last example that I wanted to take a look at. And somebody in one of my other classes today brought up an interesting point. So I have 9 to the 1/3 power times 81 to the 1/3 power. Okay, so neither of these is a perfect cube, right? And I'm asked to simplify the answer. But one of the things I do recognize is that I'm multiplying here. So if I can multiply powers with the same base, I'm in great shape because then I can add exponents together. Why does that even matter? Well, if I recognize that 81 is 9 squared, I can rewrite it this way. And again, nowhere in the directions does it go, oh yeah, rewrite 81 as an expression with a base of 9. This type of problem, one of the things that you're asked to do is kind of the detective work to recognize that. Right? So once we have this, we need to simplify here. I have a power raised to a power. So this is 9 to the 2/3, 9 to the 1/3. Now I can add the powers. 9 to the 1st, which is just 9. So an interesting thing was pointed out in one of my classes. Another person said, you know, this is really like saying the 3rd root of 9 times the 3rd root of 81. What if you went ahead and multiplied these two things together? Recognizing 81 is 9 squared, now I have the 3rd root of 9 to the 9, which, go ahead and multiply that out if you want 729, I think. But now I'm taking the 3rd root of a perfect cube, which is just 9. So this is another way to think about the same thing. We're going to use this skill a little bit later on in the year in another unit. So I definitely want you to recognize this ability to change the way that you write an expression by changing its base, recognizing it's a power. So I'm hopeful that walking through these examples and putting them on video for you helps this to make a little bit more sense, if this makes sense for you.